No, not to forget, let me thank the organizers again. It was very interesting program overall, and also, yes, but I try not to forget important things. So it's lecture 4 of my course. I will shortly recap the first 3 lectures. And this is, I think, copy-paste from the previous lecture 3. So we are speaking about Nijenhuis geometry. The background structure is 1-1 tensor with Nijenhuis identity. And in the first and second lecture, I tried to give, sometime even with attempt to prove, result in pure Nijenhuis geometry with no additional structure involved. So I did had application in other branches which previously appear without even mentioning the word Nijenhuis or even without mentioning the word 1-1 tensor. As application in the first 2 lectures, I consider theory of projective Riemann metric, and then the same object is geodesically compatible metric to a Nijenhuis operator. We did get some local results. We did get some global results. In lecture 3, I changed the direction of application and start to speak about systems of hydrodynamic types. This is also the content of this lecture, so I will recall you the definition. And we started with a system constructed by Nijenhuis operator. And we have shown that the system, which is a system of PDE, so normally such systems are very hard to solve explicitly. The most one can hope is just to prove existence, maybe uniqueness, maybe stability, but it is a big whole solution. In this case, the system can be solved explicitly, well, explicitly not in quadrature. The solution requires only integration of closed one form and solving system of algebraic equations. This integrability is based on the constant conversion law, which is natural differential geometric object associated to Nijenhuis. Differential geometric means that it is not algebraic, so also involves derivatives. So it's actually a solution of some system of PDE with data given by Nijenhuis operator. So in the infinite dimensional systems, system is any PDE is infinite dimensional system. You have infinite many freedom to choose the initial data. Conservation laws play the role function constant of solution. This is what I kind of even proof. And then for any hierarchy of conservation laws, we construct one solution. And then I formally have given, maybe it was too fast, but at least I pronounced it, that we have sufficiently many conservation laws in order to find all solutions of the system. Well, not all, almost all, but everywhere dense open set of solution, which is probably the best scenario one can get. So the goal of this lecture will be philosophically to repeat the message of the previous lectures. So I introduce and apply one more natural differential geometric object associated to Nijenhuis operator. I call it symmetry. Of course, definition will be given. So in the case you just wanted to know something which was tried by other people and which was a big or is a big topic, I will explain Tsarev-Hologrov method and even give the sketch of the proof. So Tsarev is a person, he still lives, he's probably not very old, maybe not retired yet. It was his PhD and his big result, and it's really start to be a big method for using symmetries to integrate a system of hydrodynamic type. We again will reduce the problem of finding solution to solving algebraic equation. This is actually the only known method to solve system of hydrodynamic type which work for sufficiently large class of systems. So this method, you don't get it for free. You need to do some preliminary work, and this method requires knowing of sufficiently many symmetries. Symmetries as I said, I introduce them, a solution of certain system of partial differential equation, which may be easier than the one you want to solve, but still the system of PDE. Well, it's linear, it's good, but it's still a system of PDE, and you kind of make the circle, yeah? You reduce one problem to another problem. So I will show that in the special case when our generator of our system of hydrodynamic type is Nijenhuis operator itself, so the system is UT is LUX, where L is Nijenhuis operator, then we can immediately construct by a formula sufficiently many symmetries. And I will show other cases when we can construct big set of symmetries, maybe smaller than we need, but still infinitely many of them, and comment on those which are interesting for mathematical physics. And I do hope to have the time to summarize the motivation of Nijenhuis geometry and possible principles of fine application. And if I have too many time, I will have time to thank the organizers once more, so they complain that I do it too much. So this is the definition of systems of hydrodynamic type, which you already have seen. I did it kind of with more coordinates. Unknown function are use, yeah? They're a function of two variables. X is again one-dimensional variable, and the formula is derivative by t. T downstairs is the derivative, is the matrix which may depend on u, but does not depend explicitly on t and x, multiplied by derivative of u by x. So this is kind of PDE system, but in fact, this gadget, this matrix, naturally is a 1-1 tensor on the n-dimensional space with local coordinate u's. Because if you make a diffeomorphic coordinate change, then the system remains to be a system of hydrodynamic type, and the new A tilde is just 1-1 tensor transformation law applied to the initial A tilde. So this belongs to differential geometry and not to what people do, not to theory, not to analysis. So let me now go to the symmetries. As you remember, it is the main object I would like to introduce. So in lecture 3, I try to kind of view the system as a flow, but as a flow on the set of curves. So you start with initial curve, and then the solution system, I view them as the curve parameterized by t, we changing t, we changing the curve. I don't require the curve to be, I mean, I want to be analytic, but I don't require the curve to be without self-abstraction, or it may be even trivial curves. That's fine for me. So for simplicity, I work with real analytic object. It's not completely necessary, but introducing merely smooth object will require technical details which I don't want to tell you, and which I don't understand myself completely, to be honest. So, but for this system, assuming all objects are real analytic, Cauchy-Kovalevskaya give us local system of solution. Now consider another flow. This is kind of the formula which you need to compare with this formula. U is kind of the same U, but you see that the variable is called differently, is S. So X is the same, S is differently, and instead of generator A, we have generator B. So we will say that these two flows commute if the composition of dynamical system in time t and dimensional system in time s can be applied in any order and give the same result. So on the level of PDE, it means that if you look for the both systems, this one and this one together, this would be a system of two n equations on functions which are still n functions, but now depend on two variables. One will be three variables. X is kind of a variables parameter on the curve, and one variable s, another variable is t. Yeah. Then there exists a solution of the both systems simultaneously, such that t is the variable of the first solution and s is the variable of the second solution. So it doesn't matter if we go this way and then that way, or we go first that way and this way. One way is s, another way in t, we get to the same curve. So we have seen this situation in the third lecture. I did not really emphasize it, but maybe you do still remember. So if you consider the family of n generators, I call them AI, and they are defined via this expansion. We take Nijenhuis operator, takes this co-matrix transposed. It is polynomial in L, and in lambda, and coefficient this polynomial will be called an A1. Then the system, I mean, this is now a system of n square, or maybe n square minus n, depending whether we consider x to be another variable, which is legal in this case, or just a special variable. This system is compatible. This was one of the statements I pronounced in the previous lecture. And this means that all aj are symmetry to any other ij. So we have here n-1 commuting symmetries. There are, of course, other examples. So one can ask the question, when given A, there exists B, or maybe how to check whether A and B commute. That definition was given kind of global, not to check by definition. One need to integrate, which is impossible task. But of course, any such condition can be rewritten as system of PDE. And this was done by many people, but in some situations, the most general result is due to this respectable mathematician. Svinalupov passed away already. The other two are still active. So the system is as follows. If two flows commute, then their generators commute as matrices. It is well-defined object. One tensors can be multiplied. And second condition, this is true for any vector field psi. Actually, you don't see it immediately, but it is a tensorial operation. So the output is symmetric tensor, and it should be 0. I mean, if the matrices commute A and B, and this is 0, then the A and B have symmetries. This operation is a known operation in differential geometry. Actually, tensorial operation, which include derivative, there are not much of them. More or less all of them are understood. It's called Nijenhuis-Froeliche bracket. This is a proposition, and actually I wrote here a proof of this proposition, but I do not read it. I just wrote it for your future reading. In the case there will be, I mean, the organizers will make my slides available, yeah? So I don't have time to read it, but you see that there is a proof, and there's a proof on one page, yeah? So it's not too complicated. So let me rather speak about geometry, and geometry of PDEs means that you construct similar object in the finite dimensional cases known to you from the course of analysis and possible differential geometry. So I speak about finite dimensional symmetries, and I copy-paste a part of the lecture 3. So where I said that in order to solve the flow or vector field, which is called now V, in quadratures, one needs function that are constant solution and vector fields which commute with V. There should be some correct number of the function. Actually, the number of function plus the number of V's should be n-1. We have seen in lecture 3 that analogs of function f's, which are constant solution, are conservation laws. So, and we have seen that for conservation law, the natural functional or the loop space, so functional, it is functional on our particles, which are curves, yeah, defined by the only natural way to define a function on the curve by integrating along x. Doesn't depend on t, is the same for any times t along our flow. Now, symmetries are analogs of vector fields commuting with the generator. Yeah, indeed, just another way to write down the condition that two vector fields commute is the following: the computing is the existence of the system of common solution of the following two equations. So for T1, it gives the flow of V1. For T2, gives the flow of T2. And this common solution means it doesn't matter whether go and learn T1 and then T2, or first T2 and then T1. So in the finite dimensional case, we have seen we need to know a lot of object well, n-1 object to integrate the system. And finite dimension, you probably expect to see n-1 objects as well. And n is infinity, so you may expect to see infinitely many objects. Here is strange phenomena which myself, I had difficulties to understand it. So differently from the finite dimensional case, in order to find one solution of the system, one needs to know only one symmetry under some non-degeneracy conditions. So because in finite dimensional case, we need to have many objects, so altogether n-1. To find all solutions, we need to, in finite dimensional, we still need many, actually infinitely many, even kind of function space dependent on functions, so space where we can specify arbitrary functions. But in order to find one solution, one needs only one symmetry. I will discuss this later. This will be essence of the Tsarev-Khodogrov method. Let me recall that in lecture 3, we also need only one conservative law to find one solution. Yeah. So the kind of point was that we have enough conservative laws to find all solutions. So now I came to kind of main non-Nijenhuis part of my talk, which is a very effective method, the only one which possible to use in this situation is due to Tsarev. It's called Khodogrov method, and the name this clever people chosen are stupid. It has nothing to do with Khodogrov as you see it from experimental physics. Yeah. Well, I don't really know why it's just this name. So I will first explain it in the simplest example, and then kind of modify the formula, and then let the proof for your exercise, but it will be the same in the simple example. The simple example is the Hopf equation. So in this case, dimension is 1, and the equation is derivative of u with respect to t is a u of x, a dependent on u. It is, of course, system of hydrodynamic type, but it's not a system because it's only one equation. So how to solve it? So take an arbitrary function b and consider the following relation. X plus t a of u is b of u. A is kind of data, b is the freedom you can arbitrarily choose. Now, we solve this relation with respect to u. It is one algebraic, I mean, a and b are functions, but algebraic in the sense that it's one functional equation on unknown function u, where xt and, of course, where xt are known. Yeah? So it's one equation, and as a known, I take u. So I hope that everything. Can you check that it works properly? Working, yeah. So yeah. So of course there may be some conditions for resolving. But I mean, stupid case if a and b are both constant, then you cannot do it. Yeah. But just in normal case, resolving this implicitly at least give us function u, which is function of t of x, because t of x was inside the equation. I claim that this function is solution of the Hopf equation. And let me prove this claim. So I take this guy and differentiate it with respect to x and t. So differentiated by x give us this one. You see that I differentiate a by the rule of differentiated of composed function, the same as b. Differentiated by x give, this is given by x, this gives differentiated by b. So these two equations I view as a system of equation on ux and ut, and I simply just rewrite it algebraically. So the structure of the system is clear. And then if you just rewrite it this way, you see that ux is aut, because these two coefficients are the same as required. So choosing a function b, we get a solution of this, and the set of solution is big enough to cover all possible solutions. So we are done. This is solution of the Hopf equation. Yeah, of course. Yeah. So this b is such that for t equal to 0, it, yeah. So b actually initial condition that b is equal to x. So so it's not initial condition really. So it is don't know additional velocity. So it is yeah, it's like slightly more. So, but now the statement, the observation, I mean, it's great observation indeed. So it's really changed the field, but I do it trivially, yeah. So it's just so consider consider the system harmonic type, and let B be its symmetry. Now suppose U of Tx satisfies the matrix relation. So I try to use the same letters, so you may kind of see the similarity between two equations. Then U is solution of our initial system. Yeah? And the proof is virtually the proof which I have given to here. There is some matrix manipulation in the proof, but otherwise it is the same. Yes. So you mean article B? We assume that B is a symmetry field, and then one can construct solution. So let us now discuss. So I mean, to construct solution, we need actually solve this system of equation on the variable u as function of x and t, and the system depends on our choice of b. So let us just discuss how to solve it. It would be trivial algebra. So everything which comes in the box is one I repeat from the previous slide or the previous slides. Yeah, this is the formula which I discussed. And now remember, one of the conditions in the definition of symmetry was that the B commutes as matrix with A. Yeah. Since A is G regular, okay, we assume that it is G regular, the space of matrices commuting with A is n-dimensional and coincide with the space of polynomial of degree n-1 of the matrix n. So C is arbitrary coefficient. Taking the coefficient, we take a matrix commuting with A, and every matrix commuting with A, provided A is G regular, has this form. So this is a linear algebra statement, and I simply kind of recall it in the two example. Say if the example is diagonal, doesn't matter what stays to diagonal, I put 1, 2, 3, put on the different eigenvalues. Then any commuting matrix also diagonal with any numbers row you put here. Is A is general block, so zeros here are not important, so it doesn't change property of commutative. Then this is so-called Toeplitz matrix, are matrices commuting with general blocks. And if you have many blocks, some of them probably one-dimensional, so diagonal case, some of them general, then commuting matrix have the same block diagonal structure. So we do have. Then it's not regular, and we are not. Regular means that the blocks have different eigenvalues. So the assumption regularity is indeed important for Tsarev method. And I am actually a newcomer to the science, but I kind of try to attack the experts, including those whom I mentioned today. And they, I mean, I don't complain about the colleagues. So this system we change, and B is given by this form where C's are, well, I mean, they depend on U. Why? Because A and B depend on U, and C's are just actually the data which gives B. So any B which commutes is given by this data. So and this coefficients are unique. So basically, this system, if you plug this B, an equation of n-equivalent functions. It means that Cn-1 is 0. I mean, C0 is x, C1 is t, and all other are kind of 0. So an equation of n-equivalent functions, and by implicit function theory, there exists solution for generic data. So solving the system gives U, which is solution. And it is having, if A is given explicitly, it is really, oh, sorry, if B is given explicitly, this is really solution quadrature because we really reduce the PDE problem to solving system of functional equation. So let me kind of, looks brilliant, it did very strong result. Let me give a bad example. The example is the one I have already put once on the screen, and it is example coming from mathematics is study of polynomial integrals for geodetic flow of surfaces. Extremely classical stuff. In fact, one of my old backgrounds. So when I saw the method, I immediately was very optimistic that finally I solved the problem which I first considered when I was a third-year student. So let me recall it on the level of system harmonic type. It is any of many equivalent ways to write equation, and it is a system harmonic time. I put here n equal to 3, but it's a phenomena. It works for any degree of the polynomial. It is simply some special matrix A. Now this A is explicit, and one can analyze it. In particular, one can show that it is Tsarev integrable in the sense that it has sufficiently many symmetries. For any initial data, one can tie a symmetry which satisfies correct formula on the initial data. It is actually a new result. Maybe the years, or no, years wrong. It's 2011, 2012. So it's not 20 years ago, but 10 years ago. But still quite old. But unfortunately, though theoretically the symmetries exist, there is no formula for symmetries. So no formula is not mathematical statement. Nobody found the formula, and some people tried, and I tried as well. Yeah. So though the symmetries exist, they do not really help to find solutions. And this is indeed exam situation where we kind of reduced a problem to a probably equally complicated one. I'm still keeping trying. But yeah, it is indeed one of my hidden motivation behind the whole story, including Nijenhuis geometry. So in this case, Nijenhuis geometry naturally comes, but it's still the kind of my dream and not any result. But it was example showing that Tsarev method is not always effective. So ineffective if, of course, there is algebraic condition, a generator of system should be regular, but in addition, one should have a way to produce sufficiently many symmetries B. So if you want solution with initial data U equal to identity, then one should be able to B such that X identity plus 0 is B. So we need a symmetry having, being identity on the initial data. So this is condition. This is what you're asking about in dimension one. U hat is the initial curve. So the equation on B is a linear system of PDEs of second order of B. The system was co-written, yeah. I mean, yeah, it is just since B commutes with A, one can write down the system on the coefficient of the of B. The system is overdetermined, sometimes not compatible. Compatibility conditions are well understood, so it is one can read by A when the symmetries exist. So Tsarev himself did it in the diagonal case, so in the diagonalizable case. The result of Pavlov, Sharipov, Shinalyov, I mentioned, did it by invariant formula, which applied to any matrix A, not necessarily in diagonal coordinates, and we slightly refined it quite recently. So yes, I think the names are here. Joint paper with still Andrei Konyaev, but also with some other guy, Jonathan Press. So this was a algorithmic way to understand by differentiation, algebraic manipulation, whether system is compatible. So given A, we do answer by Maple without any, so it's really answer by Maple if you do some differential expressions and comparison with 0, where the system compatible, but still we don't have formula for B. So mathematician may go, so you know this standard joke, difference between physics and mathematics, yeah? Physicists solve one problem and try to find method. Mathematically have method trying to find problem where it can be applied, yeah? So for mathematician, one can really, having a method, look for problem where the method of applicable, and in this context that let us construct a big family of systems of trigonometric type for which we know symmetries. So then we can solve them, and then let us look for physical system which can be, where this method can be applied. And this is where Nijenhuis geometry comes. Before it, you know Nijenhuis geometry. So it is the result, one of two results. So suppose L is Nijenhuis operator. Then for any real analytic function f, these flows, so generators are given by this form, pairwise they commute. I think somebody asked us what is function applied to operator. For analytic function, it's not a problem. Just polynomial applied to operator is well-defined object. Analytic function is just you do polynomial, but do not stop at some point. Just do a power series. But in fact, this guy is well-defined also if f is a smooth function. But then, I mean, in this case, one may have some singular point where eigenvalues bifurcate. But if they don't bifurcate, it is actually well-defined object, even in the smooth category, is given by formula. In linear algebra, sometimes called spectral decomposition theorem. Yeah. So in the combining this result with f gives us enough information. They give information for almost every initial data, and the theorem implies that we can solve the equation ut equal. So we generate an Nijenhuis operator itself if generator is G regular in quadratures. So it is one example. Let me give another example, and this is the following. It's again theorem, and this is another example. And another example is the follows. We start again with a Nijenhuis operator. our freedom is a choice of real integral function. Now it's called f small because it comes in as a formula. And the formula for generator is here. We take determinant of f of L minus lambda identity and multiply it with L minus lambda identity. The formula looks easy. If you'd like to kind of calculate generators precisely, it may take a lot of work and maybe we will manage. Even a simple function f, because say f is analytic, this would be a power extensions, and commutative operator would be coefficient in lambda, so this will be, so you will get the operator only as power series, but formula is compact and sometimes one can work with this formula without getting it explicitly. So this is another example. We again have a choice of a free function. It is smaller choice we had before because function of operator has more information as function of function, yeah. So function of operator is essentially n functions for G regular operator and for function. So we have less freedom in fact. So formally we still have one function, but we still have a lot of solutions because choosing any function f, we choose a solution. Sorry. No, not choosing. Sorry, not choosing any function f. So this operator non-commute for different function f. So in the case I kind of said this, it's wrong, yeah. But this actually equation for generic function f is infinite many equations because we can take power series of different lambda. So the following two special cases of choosing function f led to famous system. One of the choice is if f is 1 divided by square root of t. And this is actually the example we had because then this is the inverse of the inverse of this. And this guy is basically this is comatrix of no. The second case is the one we considered. Yeah, the second case is the one we considered, and this case is new. So this case is the case we actually considered in the third lecture. There was another way to integrate the system using considered quantities, but in fact one can do it in the also using symmetries, and there is a formula related symmetries to quantities. And this case is use the square root of t, and this example corresponds to so-called dispersions coupled KdV system of equation, which appeared in many mathematical physics literature, sometimes in the relation to physical phenomena. So there are wave equations which they describe normally asymptotically small wave equations. So it's not just a more general one, but these two cases were studied. And this case I already mentioned studied in many interesting physical structure and contribute to so-called finite zone solutions. They call it sometimes finite zone potential. I don't have understanding why these two choices, I mean, one can choose f arbitrary, but we do choose are physically interesting, maybe because nobody studied other choices, maybe because there are other reasons, but I will try to make some argument on the next slide. So why they may be physically interesting, why these choices appear to be physically interesting? Well, one of the reasons that one generally expects, because one hopes that nature is harmonious, that physical systems do not form singularities. It is known, it is actually old result of Rozhdestvy-Starenko, that the system with ft equal to t does not form singularities. They call it differently no gradient catastrophe. Yeah, but it is just basically that the solution kind of survive for infinitely many time. It is not trivial statement. You know, with PDE sometimes you have singularities even if you take the trivial PDE with Hopf equation, then actually it always forms singularity in finite time in theory. Now the special feature of the other example with 1 divided by square root of t is that it is bi-Hamiltonianable. I do not explain the word, but actually one can view infinite dimensional vector field construct as a skew gradient of functional in some infinite dimensional Poisson structure. Hamiltonicity is a physically important property. Most systems which are found so far, which are physically interesting, are Hamiltonian. So the system for the choice of E appear to be interesting, and one can show that actually only this choice gives us big Hamiltonian structure. So maybe there are more Hamiltonian choices, but big Hamiltonian give us only this choice. So I still have, I think, something like 10 minutes. Yeah, something like 10 minutes. So let me go to the long conclusion. So the first method I pronounced in the introduction, the first lecture, this is Nijenhuis geometry, is natural object to study mathematically. Let me repeat the arguments. So most differential geometric structure defined by tensor field with two indices, maybe up, maybe down, whose which satisfy some algebraic differential condition. Those defined by bilinear forms on the tangent and the cotangent bundle are well studied, and each of them gave rise to a geometry which is in mathematically with many applications. So symmetric linear form remain geometry. Symmetric linear form like geometry. Symmetric linear form on cotangent bundle geometry. In which case, these two cases we have some closeness condition or Jacobi identity condition. In this case, in fact, there are also conditions, but you don't need them for definition. Symmetric bilinear form is sub-Riemann geometry. Actually, actual bilinear form gives rise to Kerr geometry because you have object symmetric and symmetric form, and you can pack them in one linear form. Yeah. Here we have strong algebraic conditions. Symmetric form should be kind of come from complex structure. It's not degeneracy, but also some relation with G, and also differential conditions. So symmetric form must be closed. So the case of one tensor is the only case left, and Nijenhuis identity is the simplest differential geometric condition of one tensor. It is a theorem proved, well, essentially by Mischor and co-author from Vienna, but formulated in Puninsky quite recently. So our vision is the follows. I mean, kind of example of applying the same step is Poisson geometry. So say before roughly 1970s, more or less every mathematician knew local description of Poisson structures at regular points and used Poisson geometry as tool in Hamiltonian mechanics. It was really started by very classic, so Poisson himself just wrote one formula. Jacobi already used Jacobi identity. So if you look on the paper of Jacobi, you see that he really used Jacobi identity many times. So he understood the importance of it. Poisson was the formula. Lie considered Poisson structure with a generator. And this is basically the Nijenhuis geometry situation before 2018. So people who met them and can use Google knew local description at regular points, in very regular points, so diagonal case. Use it as a tool in integral systems and maybe in some other topics. But then in the 1970s, two great mathematicians, Weinstein and Nijenhuis, wrote two different influential papers and then proved there and suggest program for study. So they proved splitting theorem for Poisson structure. They suggest to study and get first result on singular point and realization stability. So they also suggested to look for global structure, Poisson structure, and to construct associated structure to Poisson structure, so Poisson algebroids. It was started by Weinstein and Nijenhuis, but you know that it appears to be a science. So nowadays it's a science. So in Nijenhuis geometry, it was started slightly later. Splitting theorem is one which I discussed in my talk. Singular points, we did have some example, and we do have much more results than we managed to give. Non-Euclidean stability is completely understood in two-dimensional case. In higher dimension, it is a kind of work in progress. In global analysis, I have shown to you a few examples. There exists Nijenhuis algebraic. It's not done by us. It was done by two independent group of people. One is in Brazil, other is Italy. I should really look in their papers because I don't also understand what's Poisson algebraic, but the word was pronounced. And they have definition and they have example which we compare, and we saw that the example are very close to phenomena we have seen in our paper. So this is the citation of von Lichtenstein, who wrote a paper on 30 years of Poisson geometry, before 30 years of Poisson geometry came, yeah? So his paper is indeed of 72, I think. And you can read, so there is became active field of research during the past 30 years, stimulated by connection with a number of areas. It's indeed true, so the reduced number of areas appeared because of Poisson geometry. And this is just one of our motivation, and you're very welcome to try. So it begins the science. So it's quite possible that results which will appear within the science are easy, but then can be used much time, like Splitting theorem. Its proof is not complicated. But let me go to the Splitting theorem first. And the second message, in the second message is that Nijenhuis operators appear without we ask them to appear, they just live there in different subject. So in my lectures, I took in the first two projective mathematics, and I explained the philosophical reason why Nijenhuis identity appears there. So why the statement of Puninsky that it is the simplest, the only quadratic relation kind of implies that it must appear. Another example was analysis of phenomenomic type. There are also other examples and other mechanisms how Nijenhuis identity appear. So, you know Feynman, yeah? Feynman, it is famous mathematical physicist, yeah? It has Nobel Prize, but besides being Nobel Prize, he really did a lot of more. And in particular, he was a PR person of physics. So people make interviews for him. And once a journalist asked him, how did you manage to be so productive in so many topics? Yeah. So it's typical question where you answer something strange. Yeah. My family give me support. Yeah. What other answer you suggest? Yeah? I work hard. I have good condition. I do not produce too much, but I have luck. Yeah. He did normal answer. So the answer he gave is that in my head, I have a table such that in rows we have methods and in columns we have problems. And once I get a new problem, I put it in extra column and apply all methods I know to this problem. And once I have a new method, I put it in the extra row and apply it to all problems I have. It is quite good way to think about how to do research, because first of all, you produce quadratically many results, but second, well, systemize your approach, and second, it appears that at least what I know, I don't really know many methods, maybe 3, maybe 4, maybe 5 at most, but 5 multiplied by number of problems really gives some number of results. Let me do it in Nijenhuis geometry. So the message is that there are many problems involving Nijenhuis operator. So projective fields I mentioned, by Hamiltonian, I didn't mention, but I pronounce the words. What F structure is, I even didn't define, I don't have time for it. Weakly nonlinear, it was a system of harmonic type which we are considered in the third lectures. And let us make this table 2 dimension. In my lecture, I at least touched new results meant in Nijenhuis geometry. One of them was Splitting theorem. I hope this one is the one which is known to everybody. I spoke about singular points, and I I put it in the slides, but this was a third lecture, so I did not really kind of read the slides. And also local distribution and have separate conjugation block. So let us apply them outside of geometry. So the Feynman table has here 4 columns, and this gives us So Hanti's theorem, what was done before, and predictivity is content of my first lecture, and this actually all assume generalization. Now we go here, and well, this is output so far, yeah? So it did work, and just taking the results, combining the setup appeared diffraction, made it as possible to fill this paper. Some of them are published, some of them are not, some of them are in progress, but it's really theoretical way to produce results, and Nijenhuis geometry is well adapted to it. So I didn't forget to thank the organizers once more for the wonderful program they organized. They still organize it, but also for the wonderful lectures from which I learned a lot. And the reference link, I put them there. I put it here, but let me just keep this. Thank you very much.